Imagine a machine built with one singular chilling purpose, flying across the entire globe in mere minutes to deliver a payload that could literally alter human history. Welcome to this explainer. Today, we're diving deep into the anatomy of the Intercontinental Ballistic Missile, or ICBM. We're going to strip away the political theater for a bit and really dig into the raw, unforgiving physics, the microscopic engineering, and the geopolitical reality of mutual assured destruction that birthed one of humanity's most complex and terrifying creations. Let's get right into it. So, think about the mind-bending physics problem we're dealing with here. We're talking about hurling a payload up to 16,000 kilometers across the face of the Earth, and doing the whole thing in just a matter of minutes. Modern systems typically operate somewhere in that 9,000 to 16,000 kilometer range. It's an absolute engineering marvel. I mean, how do you actually throw something across an entire ocean with such blinding speed that literally no one can stop it? Well, the key word to focus on here is ballistic. You see, these aren't like airplanes or cruise missiles that keep their engines burning all the way to a target. Now, this is essentially the physics of a cannonball, just scaled up to an absolutely massive spacefaring degree. You use insanely powerful rocket motors to gain extreme altitude and speed right at the start, and then you just shut the engines off. For the vast majority of its trip, the missile is quite literally coasting. It's relying purely on momentum, gravity, and a highly complex, pre-calculated physical trajectory. Section 1. The 3 flight phases. To really grasp how this coasting works, we need to break down the sheer physics of this journey into 3 distinct acts. Act 1 is the boost phase. For just a few minutes, those massive engines ignite, violently pushing the missile up into the upper atmosphere. This is also when the missile burns brightest, making it highly visible to space-based early warning networks. Then comes Act 2, the mid-course phase. This is the longest stretch. The engines are totally off, and the payload is essentially just gliding through the vacuum of space. The physics here are actually pretty elegant. Since there's virtually no air resistance up there, the system preserves its kinetic energy incredibly efficiently, coasting strictly on momentum. Finally, Act 3 is the terminal, or re-entry phase, where the warhead plunges back down through the Earth's atmosphere at hypersonic speeds. Now, going back to that initial boost phase for a second, we have to talk about the physics of mass. Rocket engineering is fundamentally a relentless war against dead weight. To carry all that fuel, you need a heavy structure. But once the fuel is burned up, carrying the empty metal tanks just wastes energy. That's where stage separation comes in. By physically dropping off those empty, heavy fuel tanks mid-flight, the missile drastically reduces its mass. The remaining thrust is now pushing a much lighter object, which exponentially increases its acceleration and energy efficiency. By shedding that dead weight, the remaining payload gets whipped up to hypersonic speeds, way beyond the speed of sound. Section 2, Surviving Extreme Physics. To understand how the payload survives this incredibly violent launch and return, we have to look closely at some microscopic engineering. Think about the absolutely hellish environment a launching ICBM goes through. Deafening acoustic pressure, crushing G-forces, violent vibrations, and massive temperature swings. To protect the fragile electronic brains inside without making the missile too heavy, engineers rely on high-strength metal alloys and highly advanced composite structures. And remember that brutal re-entry phase we just talked about? Surface temperatures can reach thousands of degrees. To survive that, they use specialized thermal coatings and advanced heat shields. These shields actually ablate, meaning the material literally burns up, vaporizes, and peels away on purpose, carrying the intense extreme heat away with it so the warhead inside stays perfectly safe. It's very similar to the tech that brings astronauts back to Earth. Fuel is another massive piece of the puzzle. Historically, liquid fuel systems offered some really specific structural and energetic advantages, but the trade-off was terrible. They took a very long time to fuel up right before a launch. Solid fuel completely changed the game. Because it's pre-packed and chemically stable, it offers a huge strategic edge in prep time. You can launch a solid fuel ICBM in a matter of minutes instead of hours. That rapid deployment is absolutely crucial if you're trying to get your missiles in the air before an incoming enemy strike can blow them up in the ground. So let's talk about targeting. How in the world does a missile traveling completely blindly through space manage to hit a target a whole continent away? The secret is the Inertial Navigation System, or INS. This is essentially the missile's brain. First, highly sensitive accelerometers measure exact changes in velocity. Next, gyroscopes track every microscopic shift in pitch, roll, and yaw. Then, the onboard computer continuously crunches all this data to calculate exactly where it is in space. And the craziest part? It does all of this without ever looking outside. It doesn't rely on GPS or any external signals that an enemy could jam or destroy. It just constantly asks and answers, where am I, how fast am I going, and which way am I pointing? Thanks to decades of relentless advances in processing power and sensor tech, we measure this accuracy using something called CEP, or Circular Error Probable. Over the years, that target radius has shrunk dramatically. What started out in the early Cold War as a pretty blunt instrument that might literally miss its target by miles has evolved into a highly precise delivery system. It is honestly fascinating, and a bit terrifying, how engineers managed to turn a city-wide margin of error into the capacity for a surgical strike from half a world away. Section 3, the MIRV revolution. Now, the technology obviously didn't stop at just making these things highly accurate. A massive, ominous leap during the Cold War rewired global security forever. Enter the MIRV, the Multiple Independently Targetable Re-Entry Vehicle. Instead of one missile delivering just one warhead, MIRV technology allowed a single launch vehicle to carry multiple, completely independent warheads. As the main missile coasts through the vacuum of space during that mid-course phase, it can actually maneuver and drop off these individual warheads on separate trajectories, aiming them at totally different targets. Suddenly, a single launch could devastate several different regions at once. This completely overwhelmed traditional defense concepts and totally broke the global strategic balance, turning nuclear war into an unwinnable numbers game. Because of MIRVs and the sheer hypersonic speeds involved, modern deterrence is no longer just about who can build a longer-range missile. It's turned into a frantic, high-stakes technological race between sophisticated early warning radar networks and offensive countermeasures. During that mid-course glide in space, modern ICBMs don't just sit there. They release dummy targets, decoys, and electronic jammers just to confuse the enemy's radar. It creates this incredibly complex, high-speed dance where space-based tracking systems are desperately trying to distinguish the real incoming threat from a giant cloud of metallic decoy balloons. Section 4, Platforms of Deterrence. Okay, so we've got this devastating technology, but how a country hides and actually launches these weapons is just as critical for strategic deterrence as the missile itself. This table lays out the nuclear triad perfectly. First, you have fixed underground silos. These offer massive, hardened structural protection against a surprise first strike. But the downside is, the enemy knows exactly where they are. Then you have mobile ground launchers. These survive by constantly moving around and hiding in vast remote terrains. But the ultimate trump card? Submarines. Hitting deep in the ocean depths, submarine-launched ballistic missiles offer the ultimate stealth deterrence. They're nearly impossible to track, which guarantees that even if a nation's silos and mobile launchers get completely wiped out, a devastating retaliatory strike is still coming. Section 5, Geopolitics and Assured Destruction. Let's zoom out to the macro level for a minute to see how this engineering marvel totally reshaped human history and geopolitical power. So, how did solving the pure physics of the ICBM shape the modern world? Well, building these systems required massive, state-sponsored research budgets, giant testing facilities, and decades of relentless trial and error. But this intense Cold War technological race did a lot more than just build doomsday weapons. The push to perfect the ICBM actually sparked massive advancements in computer science, software engineering, space tech, and material physics. Believe it or not, a lot of the civilian technologies we rely on every single day trickled right down from this exact arms race. But we can't forget that the driving force behind all this innovation was the terrifying doctrine of mutual assured destruction, or MAD. The grim reality of the Cold War was that the unstoppable efficiency of these missiles actually created a weird, fragile peace. The major global powers avoided direct military conflict for a simple reason. Everybody knew the cost. A launch by one side guaranteed a massive retaliatory launch by the other side, meaning total mutual annihilation. Paradoxically, the most destructive weapons in human history were built specifically so they would never be used. As this quote from our sources perfectly highlights, we are looking at so much more than just a flying tube of fuel here. The ICBM is arguably humanity's most complex and controversial technology. It sits right at the critical intersection of material science, propulsion physics, and high-stakes global power dynamics. It literally represents both the absolute pinnacle of human engineering and the absolute limit of our capacity for self-destruction. And that leaves us with a pretty chilling thought to wrap up this explainer. As the physics continue to advance, especially with the rise of new hypersonic glide vehicles and incredibly complex space-based defense networks, how is the doctrine of deterrence going to adapt in the future? When weapons become even faster, smarter, and more evasive, will the fragile peace that's been holding our world together hold strong? Or will the grim math of mutual assured destruction need to be entirely rewritten?